want to take just a little bit of time out to discuss the difference between direct and inverse variation. This is really more of an Algebra 1 or Algebra 2 topic, but it's one of these things that you're just going to come across from time to time. And even in AP Calculus, we're going to see little references to this in different places. So first of all, let's talk about the idea of direct variation. Direct variation is a very simple concept, okay? Specifically, direct variation is a proportional relationship. So for example, if I'm buying 2 liters of Coke, and let's say a 2 liter costs $2. If I buy 1 2 liter, I spend $2. If I buy 2 2 liters, I spend $4. If I buy 3 2 liters, I spend $6, and so on, okay? So we've got basically an input and an output each time. I buy 2, I spend 4, I buy 3, I spend 6. And by the way, if I spend 0, or if I buy 0 2 liters, I'm going to spend $0. That's actually kind of important here as well. And so what you notice here is very simple mathematical pattern. Each time my input is getting multiplied by 2 to give me the output. Okay, so as a result, the formula for direct variation is just y equals kx, okay, where k is sometimes referred to as the constant of proportionality. It's whatever your multiplier is, okay? And it could be a fraction, it could be negative, but in this particular case, sometimes we refer to this as the particular equation, the equation that matches this particular set of data. This particular equation would be y equals 2x, okay? So that's your basic setup. Now, as I said before, direct variation relationships are actually proportional. You don't necessarily have to have that constant variation unless you have a reason to know what it is. So you can also look at these values fractionally. 1 over 2, if you make a comparison between x and y, 1 over 2 is 1/2. 2 over 4 is also 1/2. 3 over 6 is also 1/2, and so on. So you can actually solve a direct variation problem using proportions. So, you know, for example, you might see some kind of relationship like this. You might see something like y varies directly as x. If y equals 45 when x equals 5, find y when x is 8. And you can do this a couple of different ways. Number one, you can try to write the equation, okay? So I know I'm working with the equation y equals kx here. I know that when x is 5, y is 45. So this is a 5, that's a 45. And you may be able to look at this and tell pretty easily, oh, I'm multiplying by 9 each time, okay? So my k value here is going to be 9. So my equation is y equals 9x. And then you can put your other set of data in here. What is y when x is 8? Well, 9 times 8 would end up giving us a value of 72, okay? But you can also do it with a proportion if you don't need that multiplier. So for example, I could say when x is 5, y is 45, and I could do a comparison between those two values. So I always have to get a fraction that's going to work out to be 1/9 if you wanted to simplify that down. And then you could say, well, okay, x is 8, what is y? And you could solve that, and you would end up with the same 72 there if you cross-multiplied and solved, or if you simplified it. Okay, so that's direct variation. Very straightforward relationship. And anyway, you can see other wordings. For example, if they said something like y varies directly as x squared, that would be y equals a constant times x squared. If they said something like y varies directly as the square root of x, that would be y equals a constant times radical x, and so on and so forth. So, you know, you can tweak this, and you can have other relationships. It doesn't just have to be 2 variables. You can be doing something with one of the variables. Okay? By the way, if you graph this, very key factor here, if you think about a form y equals k times x, that's a straight line equation. That's y equals mx. That's a slope times x. There is no y-intercept, okay? Direct variation lines will always pass through the origin, okay? And the slope will be whatever that multiplier was. So if it was y equals 2x, we'd have a slope of 2. It'd be passing through the origin, and so on, okay? Really important. If it's going to be a direct variation relationship, has to contain the point 0, 0. And if you think back to the soft drink example, that should make sense. All right, inverse variation. Oh, by the way, also indirect variation, you know, if I had an equation like y equals 2x, as x increases, y also is going to increase, okay? So if I put in 3, I get back a 6. If I put in a 4, I get back an 8. If I put in a 5, I get back a 10. As x gets bigger, y also gets bigger. Likewise, as x gets smaller, y also gets smaller, okay? It's that direct linear relationship there. Inverse. So inverse variation is a little different setup. The base equation they're going to give you for inverse variation is usually x times y equals k. Okay, and what that tells you is your x and your y are always going to multiply to equal the same constant value. All right. So, for example, if I have something like y varies inversely as x, if y equals 2 when x equals 12, find y when x equals 4, something like that. You can just fill those values in as well. The thing I like about this formula is it's very easy to figure out what the product's going to be. So they give me a 2 and a 12. So x is 12, y is 2. And you can see here 12 times 2 is 24, okay? So my k value is going to be 24. What this says is the product always is going to be 24, okay? So basically I could say, all right, x times y has to equal a constant of 24. What is y when x is 4? Well, 4 times 6 would give me an answer of 24, okay? This relationship is called inverse because you get a backwards relationship. If I'm going to keep getting the same product every time, as x gets bigger, y is going to have to get smaller. So if x is 1, y is 24. But if x is 2, y drops down to 12. And if x is 3, y drops down to 8, and so on. So as one variable increases, the other variable decreases, and we get this kind of reverse relationship. All right? If you graph this, you might want to solve the equation a little differently here. If you solve for y, you can divide both sides by x. You can also write this as y equals k over x. Some of us think of reciprocals as an inverse, so that's another relationship there. If you graph this, this is really the equation y equals some constant times 1 over x. So like 2 times 1 over x, 3 times 1 over x. K could be 1 for that matter. It could just be y equals 1 over x. If you graph these, so if I was graphing y equals 1 over x, for example, when x is 1, y would be 1. So the point 1, 1 is going to be on that graph. When x is 2, y is going to be 1/2. Okay? When x is 3, y is 1/3. When x is 4, y is 1/4. And you can kind of see here as x keeps getting bigger, y is getting smaller and smaller. Likewise, as x gets smaller, y gets bigger. So if x is 1/2, 1 divided by 1/2 is 2. So we plot that point. If x is 1/4, y would be 4, and so on. And so what you're going to get is a graph that kind of does this sort of thing. It's going to approach a horizontal asymptote here. It's going to approach a vertical asymptote here. You could also have negative values, and so an inverse relationship could also pop up in this axis. I suppose k could be negative, and that could flip things around at different positions. But that's your typical setup. So you can see here as x gets bigger, y gets smaller. As y gets bigger, x gets smaller, and that's your inverse relationship. So hopefully that gives you a quick review of that, and hopefully that looks familiar from things you've done in the past.